Hello and welcome to my lecture on James space, a topic in functional analysis and more precisely in Banach space theory. So what is James space? Well, James space is a counterexample in Banach space theory, and it was constructed by the mathematician Robert C. James. He was an US American mathematician, and he constructed this space in the year 1956, if I am not mistaken. And so what property does this space have, which makes it so interesting? Well, James space, J, is not reflexive, which isn't that interesting. I mean, that just means that the canonical embedding from J to its double dual space J dash dash, which maps any element to a functional ij of x, which then in turn maps any functional to its corresponding value at that point x. This is not surjective. However, and now it gets interesting, J is still isometrically isomorphic to J dash dash. So it is isometrically isomorphic to its double dual space. And I mean, this doesn't seem very intuitive at all. And actually, it was not thought to be possible until James constructed this notorious space. And as you may expect, it will be a rather technical lecture. It is not a very beautiful space, if I say so. It is rather ugly, actually. That does not make it less interesting, though, so I think it is still worthwhile to engage in the study of James space. I should note that this lecture follows my bachelor's thesis, which I originally wrote in German, and this thesis is like 99% of it is based on a book from Robert E. Magginson. So, Magginson. And this will be my primary source, and basically the whole lecture will follow the construction, the theory for James space, the same way that Magginson does it in his book. And if you want to check out his book yourself, it is called An Introduction to Banach space theory. So we will follow his way of argument, and this will go like this. First, we will go over the theory of Schauder bases, and here we will also, in the large majority, if not 100%, follow the same way that Magginson does it in the earlier chapters of his book. Then in the second part, we will develop a theory for isomorphisms of Banach spaces, which are kinda like the Banach space C0, which is the Banach space of sequences of real sequences which converge to 0 in R. So this will be the isomorphic theory for spaces similar to C0 R. And this similarity that this theory will rely on is that the Schauder base will be required to be shrinking and monotonic. And then finally, in the third chapter, we can finally begin studying James space by applying the previously developed theory of isomorphisms to it. And as a side note, n will be the set of natural numbers starting at 1. So 0 is not a natural number. However, I am not discriminating 0. This is for purely technical reasons. Having 0 as a natural number would at some point, make stuff more complicated. So that is the only reason we exclude it here. Normally, I like to call 0 a natural number. So shoutouts to 0. Speaking of shoutouts, before we begin, I would like to thank my wonderful advisor, Miss Jacob, a professor at the University of Wuppertal, which supervised me during my bachelor's thesis and made all of this possible. Every time we talked, it was very comfortable and it helped a lot. So yeah. And also thank you to the friend of mine who lent me this tablet for the purpose of making this lecture series. Okay, so let's jump straight into our first chapter about Schauder bases. So, what is a Schauder basis? We will begin with the first definition to clear up exactly that question. A Schauder basis or just basis for an infinite dimensional Banach space over K, which is either the reals or the complex numbers, is a sequence of vectors such that every other vector has a unique representation x is equal to the infinite sum as n goes from 1 to infinity of alpha n times xn, where the alpha n's are scalars. And this equality is to be understood that the limit of the difference from x and the partial sums of this representation approaches 0. And that limit is 0. And we define further a basic sequence is a sequence that is a basis, a Schauder basis, on its closed linear hull. So on the closed span of the vectors. Okay, and from now on we will use a shorter notation for the span and the closed span in the following way. This will denote the span of x, and this will denote the closed span of x for any set x. All right. Now, maybe I should not have called this set X as our Banach space is called X, but you get the idea, I hope. So, naturally, after such a nice definition, we want to look for some examples, and that is exactly what we are gonna do next. So, examples 1.2. And we will have 3 examples. First up, if we look at the Banach space C0 with the classical supremum norm, this is the Banach space of real sequences which converge to 0. This has the basis, the Schauder basis En, where E1 is the sequence which has a 1 at the first index, E2 is a sequence which has a 1 at the second index, and we go on like this. Secondly, I think it would be nice to note that not every sequence is also a basic sequence. And I will give an example to make this more intuitive. Consider Fn, where F1 is equal to 1/2 E1 and Fn equals En minus 1 for n bigger or equal to 2. So Fn is 1/2 E1 and then E1, E2, E3 and so on. So this is actually not a basic sequence. For example, we have that the closure of these Fn's, so the closed linear hull of these Fn's, this is equal to C0. However, C0 is not a basis. However, Fn is not a basis on C0, so it is not a basis on its closed linear hull, so it is not a basic sequence. And we can quickly verify this fact with a nice example. So let's consider the vector x, which is 3, 2, 1, and then just zeros afterwards. This is obviously an element of C0. And we can represent this with 2 sequences of real scalars. We can represent this with alpha n equals 6, 0, 2, 1, 0, 0, and on and on and on with zeros. Or we can use beta n with the 0, 3, 2, 1, and so on. And since this vector has 2 representations, the representation is not unique and it cannot be a basis. All right. And next up, another nice fact to note. Since the linear combinations of the basic vectors form necessarily a dense subset, it follows quickly that every Banach space which has a Schauder basis is necessarily separable. A nice fact to note here is that it was shown by Per Enflo in 1973 that the opposite is not true. There does exist a separable Banach space which does not have a Schauder basis. However, that will not be the topic of this lecture. I just wanted to quickly note it here. Now, since every Banach space with a Schauder basis is separable, it follows that if we have a Banach space such as L infinity with the supremum's norm, which we know is not separable, then this does not have a basis. And actually, the standard basis En, which we introduced for C0, is not a basis for L infinity. And to see that, we consider X the constant 1 sequence, which is in L infinity since it is bounded. Then we have, for all possible representations by scalars, and for all indices, we have that the norm of X minus the nth partial sum, well, this is the norm of the following vector. We have 1 minus alpha 1, and then we have 1 minus alpha 2, and on until 1 minus alpha capital N. And then what follows is 1s. And we have this in the supremum norm, so this is obviously greater or equal 1. So this does not converge to 0 as we would want it for our definition of a Schauder basis. However, let's now move on to the next definition. Definition 1.3. So let X be a Banach space and Xn be a Schauder basis of that Banach space. We define the mth coordinate functional xm dash as the following map, the following functional xm dash Now, since every vector has a representation with respect to this basis, this is well defined. We map this to the mth, well, coordinate. And this is also linear. So xm dash is well defined and linear. And we will also introduce the mth natural projection as the following. Pm goes from x to x, and it just projects a vector, and again, since every vector has such a representation, this is well defined, onto the first m coordinates, so onto this mth dimensional subspace. That's why it's called a natural projection. This is also well defined and linear. Okay. And now with this at our hands, we define a central concept of this lecture. So we let Pn be the nth natural projections. We define this following number, the supremum of the norms of these projections, and we call this the basis constant of xn. Now, we can talk of a basis constant of xn since these natural projections depend in their definition on xn, so they do contain information about that basis. And then we can, from this, call xn monotonic or monotone or orthogonal if the basis constant is equal to 1. And indeed, we get as a corollary from the definition that k is always greater or equal to 1. And you can check that yourself. It is not hard to show. Now, naturally, the question arises whether the coordinate functionals are continuous and whether the natural projections are continuous. And this is also the question whether the basis constant k is necessarily finite. And to see this, to answer this question, we will introduce a new norm. So, definition 1.6. We have X a Banach space and Xn a basis of that Banach space. The Xn monotonizing norm, or in short, just Xn norm, which we will denote as such. So we index it with this basis, is defined as or by this following formula. It is the supremum of the norms of X projected onto these m-dimensional subspaces. And we can also think about it in the following way. Since every X has a representation according to the basis, we can put in here exactly that unique representation. And so this is defined as the supremum of the partial sums. This is exactly the same thing. And the name already suggests what this norm will be doing. We can, as will be shown next, renorm a Banach space X with this new norm and achieve then a monotonic basis. So Xn will become monotonic if we renorm the space X with this new norm. And indeed, these two norms, so the original norm and the Xn norm, will be equivalent. And that will be our first big theorem, theorem 1.7. So X with some norm should be a Banach space, and Xn shall be a basis for that Banach space. Then X with this new norm is also a Banach space, and the norms are equivalent. And to show this, we will first show that this new Banach space is complete. And then at the end, we will use a nice technique to quickly show that they are equivalent. So we will take a sequence of vectors in X, and since every vector has a representation with regards to the basis, we index the scalars. So this is a double index sequence. And this is now a sequence of vectors in X. All right? And we want this to be a Cauchy sequence in the new norm. So this shall be a xn norm Cauchy sequence. And now we take two indices, j1 and j2. Now, for k greater or equal to, we find that alpha k j1 minus alpha k j2 times the norm of the kth basis vector. Well, this is the same as the following. We pull in this absolute value into the norm, and then we add a bunch of vectors in a bunch of dimensions and then just remove them again. So you will see what I mean. We will have this sum here, and then we remove the vectors of the first k-1 dimensions again. And this technique we will use again later. So why do we do this? We do this to just apply the triangle inequality. We use the subadditivity of the norm, and we get the following. This is just, well, this is obvious per definition of the xn norm. And well, indeed, xn is a norm. Maybe I should have mentioned that earlier. You can try proving it yourself. The only thing that could be considered even a challenge is showing the triangle inequality, but you just rely on basic properties of the supremum and obviously the triangle inequality of the original norm to show that. Okay, so sorry for skipping over that part, but yeah, the xn norm is actually a norm. So we have this inequality, and we also will find one for k equal to 1. And here it is, well, we just get it pretty for free. So this is just straight up smaller than the norm of this vector. Again, we just pull in the absolute value into the norm. And since in the definition of the xn norm we take a supremum, this follows trivially. Now, since the alpha and j's for all n are bounded from above by Cauchy sequences, they are again Cauchy sequences. So the alpha and j's for n element n are Cauchy sequences. And these are Cauchy sequences of scalars in the field of reals or in the field of complex numbers. And since these fields are complete, we have that the alpha and j's converge. So they converge, and we can denote alpha n to be the limit as j goes to infinity of alpha n j. And now we will show that these representations here of vectors for x goes to infinity actually converge to this vector with coordinates alpha n. So let epsilon be greater than 0. Let's take a j epsilon dependent on epsilon from the naturals, such that for all j and j dash which are greater than j epsilon or equal, and for all m element n, we want to have the following. This is obviously less or equal to the following. So we have the same vectors, but now we take all dimensions of them in the xn norm. We want this to be smaller than 1/3 of epsilon. We can just do that since it's a Cauchy sequence, right? So for j equal to j epsilon and j dash going to infinity, this gives that the following is smaller than 1/3 epsilon for all m in the naturals. And we will give this equation a number 1.1. Now, it follows that for m2 greater than m1 greater than 1, we get, now we take the dimensions from m1 going to m2, alpha n xn minus same dimensions, alpha n j epsilon xn. This is the same as, and now we apply the same technique as earlier, this is the same as taking the dimensions from n1 to m2, alpha n xn minus n equals 1 to m2, alpha n j epsilon xn. And then we remove these new dimensions again. So we go from n1 to m1 minus 1 of the same vectors. This is just the same. And now we can again apply the triangle inequality. So we get the following. And now we can use our inequalities that we obtained earlier and just say that this is less or equal to 2/3 epsilon, since both of these are less or equal to 1/3 of epsilon. All right. And additionally, we can find an m epsilon such that for m2 greater m1 greater m epsilon, we have that this is less than 1/3 of epsilon, and then we can finally put this all together. In total, we get that the norm of this vector, which is, by using the triangle inequality, the same as the following: 2 alpha n j epsilon xn plus the norm of going from n equals m1 to m2 of alpha n j epsilon xn, where this is less or this is just less than epsilon, since this is less or equal to 2/3 epsilon and this is less than 1/3 epsilon. So this is less than epsilon, and we can conclude that this sequence right here is Cauchy in the original norm. Now the Banach space is obviously complete, so this converges. And since the inequality that we gave the name 1.12 also holds for j greater than j epsilon, we get that the norm of this vector alpha n j x n minus alpha n x n in the xn norm, which is just the same as the supremum over the projected versions, this is just less than 1/3 epsilon and thus obviously less than epsilon, and we can conclude that this does actually converge to this. So here we take obviously every single dimension, and this converges as j goes to infinity, which is what we wanted to show. So the new Banach space, the renormed Banach space with the new norm, is complete. Well, so it's a Banach space. It was a normed space before. Now it's a Banach space. Okay, and this was the main part of this proof. We also wanted to show that these norms are equivalent. And here we will use a nice technique. We consider the identity map, which goes from our new Banach space, so with the xn norm, to the original Banach space, so x with the original norm. We just use the identity. Now we have that the original norm is smaller than the new norm. Thus, I is bounded. And obviously, I is a bijection. I is bijective. And then it follows from the open mapping theorem. So this is the open mapping theorem, that the inverse of the identity is also bounded. And thus, there must be a constant such that this norm is smaller than that constant times the other norm. And now, with this and this, we can conclude that the norms are indeed equivalent. And we finish the proof. Nice. So that will be it for this part of the lecture. And we will continue with the theory of Schauder bases in the next one. Bye bye.